Okay, today we're going to be reviewing something that you should have learned very well in Algebra 1 that is going to be a very important part of what we're going to do in Chapter 5 as well as the remainder of the second semester as we go through some other chapters. Today we're going to be reviewing the process of FOILing and factoring polynomials. Now, to start, this is going to require us to do a quick review of polynomials and learn a little bit of the terminology that you need to be familiar with as we move forward. So if we take a look here, as we start, we have a list of common types of polynomial functions that we're going to be dealing with, and we need to talk about the various parts to them. Now, each type of polynomial that we deal with has a specific name that goes along with it. So you can see in the type we have a constant function, a linear function, which we dealt with, and if you look at those two, these are basically Algebra 1 functions that you've learned. In Chapter 5 we're going to be dealing mostly with quadratic functions, and then we'll introduce the idea of a cubic and a quartic function to you later in the semester as we move forward. But before we get started with the very specifics, we need to talk about the different parts of a function. Now we have three different terms that you need to be aware of: the leading coefficient, the constant term, and the degree. Now, before we can figure these out, we need to be able to take the polynomial function and write it in standard form. So I'm going to just give you an example here. If I take a polynomial function like 2x squared plus 3x plus 1, this is a quadratic function because it is to the second degree. It is written in standard form because the exponents are in descending order. So let's take a look at all these parts. If we take a look at this, the leading coefficient is the coefficient in front of the initial term. So 2x squared is our first term of this polynomial. The 2 would be considered the leading coefficient because it is the coefficient in front of the first variable. Now, the degree here is the highest exponent. So remember, the degree is the highest exponent. And when we are finding the degree, if it's written in standard form correctly, it should be the initial exponent all the way to the left. And you notice that as you go down, they get less and less. Now, this degree indicates to us the type of function that it is, and the type of function for this case is a quadratic function because it has a degree of 2. So you can see that when it's written correctly, it's very easy to tell what type of function you're dealing with when it's written in standard form. Lastly, we have the constant term, and the constant term is the number that does not have a variable associated with it. So the 1 in this case is the constant term. So before we even get fully into multiplying polynomials and factoring polynomials, you'll need to be very clear on the different parts, how to write a polynomial in standard form. You will be tested on these things, and so you need to have a good working understanding of them. So, as we move forward, we can take polynomials, any type of polynomial functions, and we can multiply them together. Now, as you learn to do this in Algebra 1, you probably learned how to deal with binomial expressions, which are terms that have two terms in the expression. So if you recall, we have a term where you can have one term, so 2x, that would be called a monomial. You could have something like x plus 2, and that would be a binomial. And then, of course, you could string that out to have 3 parts or 4 parts or 5 parts, and so forth and so on. What you may recall from Algebra 1 is when we multiplied something, we could multiply a monomial times a binomial, and this just required the distributive process, so it'd be x times x and x times 4. And that was just simply the distributive process. Then you may have moved up to something where you use the term FOIL. Now FOIL is just an acronym that gives us the order in which we want to multiply binomial expressions. And so if you remember multiplying binomial expressions, we had to take this and do it in a certain order. And you can see that the letters represent an ordering process in which to multiply by. Now, this is convenient when you're multiplying two binomial expressions, but it does not work for anything bigger than that. So if you're multiplying a monomial times a binomial, it's just a distributive process. If you're multiplying something bigger, it's still the distributive process, but it's convenient for us to use the FOIL terminology when we're multiplying two binomials. Now, what you need to keep in mind here is that this is simply still the distributive process, but we're going to be going through it twice. So if you look at the F and the O part, we're going to do the first part of each binomial. That's going to have me multiplying x times x. Then we're going to multiply the O part, which are the outer terms, which is the x and the 5. So if I multiply the x times the 5, what you recognize here is that I've simply distributed the x to the entire x plus 5. So I've done the distributive property one time there by doing the F and the O. Now, to continue the FOIL process, we are going to multiply the inside terms, and this has me multiplying the 3 times the x, and then the last terms has me multiplying the 3 times the 5. And if you recognize, what we've done here is we've done the distributive property a second time. So FOIL is just really a fancy acronym that gives you the order of distributing the binomial twice. So if we take a look at this sample problem, what I'd like you to do is take a little time, pause the video, and work sample problem 1 on your own, and then you can start up the video again to see the solutions. So go ahead at this point, work sample problem 1 using the FOIL method to multiply those two binomials. Okay, so if you did the sample problem, it should have looked something like this. We'll start with the distributive process of the x first, which is the F and the O of the FOIL process. So x times x is x squared, and then x times negative 1 is negative 1x. Then the second process is to distribute the 2, which gives us a positive 2x and then negative 2. Now, once I've distributed both parts and completed the FOIL process, it's important that I combine like terms. Now, understand that x squared and x are not the same terms, so you cannot combine those. The only terms that we can combine here are negative 1x and a positive x. So when we do that, that gives us x squared plus 1x minus 2, which is more appropriately written as x squared plus x minus 2. And that is my final answer. Now, a couple points about directions here. You could see something like simplify, or you could see something that says to multiply the polynomials, and they basically mean the same thing. So we're just trying to combine the two parts together, and we finish here with a 3-term polynomial, which would be a trinomial, and these are terms that you should be familiar with from Algebra 1. Now, that is when we're going to take two smaller polynomial expressions and put them together. If you recall from Algebra 1, we also had a process called factoring polynomials. Now, factoring polynomials was taking a bigger polynomial expression and breaking it down into its smaller parts. Now this is the opposite of actually multiplying polynomials, and if you recall probably from middle school, a process called prime factorization. So if we took a number like 18 and we broke it apart, we would get something like this, 2 times 9. And then you can see here that the 9 can be broken apart a little farther. So we have 3 times 3. Now in the prime factorization process, this 2 is still part of the initial problem, so we have to bring it down. And this creates what we call a factor tree. So the prime factorization of 18 would be written as 2 times 3 squared. In essence, this is what we're going to do when we factor polynomials. We're going to take the polynomial expression and we're going to break it apart into its smallest parts possible. Now, we're going to start here. Factoring can take place in one of many ways. We're going to start with the more simple problems and build up to the more difficult factoring problems as we go along. So, and be sure to do the sample problems as we go through this video so that you can get the practice as well. Now, if we look at our first situation here, we're going to do what's called factoring out a common monomial. In essence, we're looking for the greatest common factor. So the GCF, we're looking for one number or one expression that is common between everything inside the polynomial, and we're looking to take it out. So if we look at part A, we have 5x squared minus 20. Now 5x squared minus 20, between these two terms, they both have a 5 in common. So we're going to reverse the process of distribution, and we're going to pull out the 5 instead. And you can see when we take the 5 out from 5x squared, we're left with an x squared. And when we take a 5 out from negative 20, we're left with negative 4. Now, this starts the factoring process, but keep in mind that we are not necessarily finished here. Just like when we were factoring 18, when we broke it up into 2 and 9, there was still the 9 could be broken up into smaller parts. Same thing with part A here. When we take the 5 out, we're left with x squared minus 4, which can then be broken up into 2 smaller parts as well. Now x squared minus 4 is called a difference of squares, and we will discuss that in much more detail later on in this video. So what I'd like you to do now is just take a look at example number 1, parts A, B, C, and D, and look at the different ways that you can factor out common monomials, and then I want you to work the problems in sample problem number 1 by factoring out the common monomials. Now keep in mind, each of these samples could be factored farther, but at this point in time, all I really want you to focus on is factoring out the common monomial and getting practice at that. We'll worry about factoring the other types a little later in this set of notes. So go ahead and pause the video now and take the time to work sample A, B, C, and D. Okay, so if you've done the sample problem A, B, C, and D, you should have worked the problem similar to what I'm going to do here. But look at part A, 14x squared minus 2x minus 12. The common factor that each of these terms has is 2, so we're going to take a 2 out in essence. So if we take a 2 out, what's going to be remaining from the 14x squared is 7x squared. What will be remaining from the positive 2x will be a positive x. And what will be remaining from negative 12 is a negative 6. So in essence, it's like dividing each of these things, each of these terms by a 2. Now keep in mind, if you divide by 2, that's fine, but you're not losing the 2. We are basically just factoring it out. It's just like up here, if we divided 18 by 2, we would have 9 left over, but we wouldn't lose the 2 in the process. It's up one of the smaller factors. So we do not want to lose the 2 in this process as we go along. Now, just as I told you earlier, some of these may be able to be broken into smaller parts. So we may be able to factor this into smaller parts, but we will focus on that later on. If we look at part B, we look at 3v squared minus 18v, and we notice that both terms have a 3 in common, but they also have a v, so we need to pull out the full term that they share to factor this completely, which would involve pulling out an entire 3v. Now when you do that, you're going to be left with only a v from the 3v squared, and in this case you're going to be left with negative 6 from the negative 18v. So 3v times v minus 6 is fully factored here. Now, part C, we can look at this again and see that 12x squared plus 3x plus 3 each have a 3 in common, so we're going to factor out the 3. And again, it's just like dividing 3 from everything, but we can't lose the 3, so we're going to be left with 4x squared plus x plus 1. Again, there is a possibility that that could be factored farther, and that is something that we will be dealing with a little bit later in this video, and something that you always want to be aware of, that there is a possibility that you may have more factoring to go. Now as we go to part D is actually a special circumstance. On its own, 4u squared minus 36 is called a difference of squares again. So it can be factored directly from that using the difference of squares method. But again, we're going to focus on difference of squares later in this video. So what I want you to work on here is just simply pulling out the common monomial. And in this case, 4 is the common monomial, which is going to leave us u squared minus 4. Now, we get to 4 times u squared minus 4, and we can see here this is also called a difference of squares, and it can be factored a little bit farther as well. And again, if you factored any of these farther, you're ahead of the game at this point, but we will be expecting you to do that by the end of the set of notes. Okay, so there we factored out common monomials, and that will be the first step that you would probably look for when factoring polynomials, so that you can make some of these problems a little bit easier. Now, let's move into something that's a little bit more difficult, factoring trinomials. Now, in the process of factoring trinomials, assuming that we cannot factor out a common monomial first, we are going to have to break a trinomial up into 2 smaller binomial parts. Now you can read through the beginning paragraph and see that when we do this, we're basically going to be breaking it up into going from a trinomial to start and finishing with 2 binomials to finish in the factoring process. Now there's a pattern that takes place here that you're going to have to become aware of. The outside term, the constant term, is going to be a result of the products of the 2 binomials, and the inside term is going to be equal to the sum of the particular variables from the binomial. So we have to come up with a list of potential pairings that we could use that would make a product and a sum given the m and the n values from the binomial. So what we want to do when we work a problem like this, and we're going to start by clarifying that we are only going to be doing this with a trinomial that has an understood 1 as a leading coefficient. That's a very important part of this, because when we have a number greater than 1 for the leading coefficient, we're going to go through a different process called grouping that we'll discuss later in the video. But we want to focus on right now our leading coefficient will be equal to 1. So here, if you look at this first example, example 2, we can see that we have the number 28, or better yet, we have the value negative 28. we want to come up with all of the possible combinations of numbers that would multiply together to give us a value of negative 28. And so if we did this in table form, you could see here we've come up with all of the factors of negative 28. So negative 1 times 28 is a negative 28. A positive 1 times negative 28 is also negative 28. And so forth and so on until we come up with every single pair of factors that multiply to get negative 28. Then we want to look through that list of factors and we want to see which set of factors, when added together, would give us the negative 12. And so we're looking for two parts here. We're looking for the m and the n that could give us a negative 28 when multiplied together, and the m and the n that could give us a negative 12 when added together. And that particular situation is only satisfied with one set of numbers. That is the 2 and the negative 14. So what happens here is we can take the 2 and the negative 14 and use those in our binomials, and you can see that the x squared minus 12x minus 28 factors into two smaller parts of x plus 2 and x minus 14. Now, if we wanted to check this and see that we did this correctly, we would simply take the two binomials and then FOIL them back together. If we did this properly, the FOIL should bring us back to the original trinomial. So x times x is x squared, x times negative 14 is negative 14x, 2 times x is a positive 2x, and 2 times negative 14 is negative 28. If I combine my like terms, that gives me x squared minus 12x minus 28, which we see was our original trinomial. So that clearly gives us some indication that we factored each of these, it factored this trinomial properly to the two binomials necessary. Now, the more and more factoring that you do of trinomials with the leading coefficient of 1, the better you'll get at recognizing the factors that multiply to give us the constant term and then add together to give us the middle term. So this is an experience situation that requires you to get lots of practice, which we will do in class. It's very important that you do this and learn how to use your calculator effectively as well, so that you can quickly determine the factors that multiply to get the constant term. So if we look at the sample problems, sample problem 2 has two trinomials with a leading coefficient of 1 that we ask you to factor. So what we're going to want you to do is to come up with all of the factors of negative 48 for sample problem part A that would multiply to give us negative 48 and also add together give us negative 2. So go ahead and pause the video at this time and work sample problem number 2 part A and B. Okay, let's take a look at this. Hopefully you've given both of these problems a good shot. If we're looking at this and we're making a list of factors, we start off with probably the most obvious parts. So I know that 1 and negative 48 are going to multiply together to give me a negative 48. But it's clear that whenever I do negative 48 plus 1, that's going to give me a negative 47, which is nowhere close to the negative 2. And of course I could always give the negative part to the 1 and the positive part to the 48, but that still gives me nowhere close to the negative 2 when I add those parts together. So this is where you can learn to use your calculator effectively and quickly. What I can do is I can go to my calculator and I can simply start by looking at the different factors of 48, and I can start this off by doing simply the next number. So 48 divided by 1 is 48. I've got those two numbers, so then I can move to 2. So I could say divided by 2, and of course I'm going to use a decimal, and that gives me 24. So that would give me the next set of terms. I would know that 2 and negative 24 would also give me a negative 48. But again, when I add those two together, it gets me nowhere close to negative 2. So what I'm going to suggest to you is this. Instead of having to write down a full list of factors, it would probably be best if you could quickly roll through these factors on your calculator. So I can do 48 divided by 4. I know that 48 divided by 3 is not going to be an even number, so I'm going to skip to the next number possible, which would be 4, and that gives me 12. So then I have to think to myself, is there any combination of 12 and 4 that would give me a negative 2? And I would see that that is not the case. So then I go to the next number. 5 would not give me an even number, so I need to go on to 6, which gives me an 8. And then here we have a situation where we have the possibility of getting a 6 and a negative 8, which would give me a negative 2. Now you have to be careful with signs in this case, which we could also have a negative 6 and a positive 8, so you would have to kind of make the distinguishment between these two values as to which one would give you a negative 2 when you added them together. And so when we do this, a positive 6 and a negative 8 gives me a negative 2 as a middle term. So I will simply take these two and break them apart. Now, we've been focusing most of our attention here on the negative 48, but keep in mind the x squared is going to be broken apart into two individual parts as well. And so what happens here, that breaks up into x and x, and we can see that the negative 48 is going to break up into a positive 6 and a negative 8, which is going to give me my two smaller binomial factors. Now, a lot of students have difficulty with this at first because they say, where did the negative 2x go? It just disappeared. And in essence, the negative 2x has been broken apart because the trinomial is getting split into two binomials, and that middle term is in essence going away. But a quick foiling of x plus 6 and x negative 8 would get you back to x squared minus 2x minus 48. So do not let the disappearing middle term alarm you. That is supposed to happen. So you can see I've gone through the slower process of writing out all the factors here, but what I would suggest to you is to become very proficient with your calculator and be able to do this a little bit faster, and then as you do more and more problems, you will be able to do most of this in your head. So as we look to sample B, I've got x squared minus 9x plus 14. So it's clear that this is going to break up into two binomials, and x, because it has a leading coefficient of 1, x squared is going to break up into 2x's quite simply. So then we need to focus on the outside number of 14. Now 14 can be broken up in a couple of different ways. We've got 1 and 14, which does not give us a combination of negative 9. So we need to come up with a situation where we could have two numbers that multiply to give us a positive 14 but give us a negative middle term. So this is a little bit different and a little bit trickier. Now, the only other numbers that multiply to get 14 would be 7 and 2, but we need to take a careful look at this. I could have a positive 7 and a positive 2 that multiply together to give me a positive 14, but that's not the only situation that I have. I could also have a negative 7 and a negative 2 that could multiply together to give me a positive 14. So then it's my job to determine which sets of these numbers could be added together and give me a negative 9x. And in this case, it is the two negatives that add together to get the positive. So I could take a negative 7 and a negative 2. And when I have x minus 7 times x minus 2, I've then factored the trinomial to its two smaller parts. And again, if you wanted to check this, you could simply refoil these numbers back together, and it should come out to be x squared minus 9x plus 14. Now, a quick word here. I've been listing sets of numbers here that could be possible factors for our trinomials. do not get these confused with ordered pairs. This has nothing to do with ordered pairs at this point. It does not represent anything on a graph. This is just me listing sets of numbers to give me guidance for my factoring. So these are the examples in factoring trinomials that have a leading coefficient of 1. So keep in mind that when we have a leading coefficient of 1, this would be the process that you would want to use in factoring. Now, what we're going to do is we're going to move on into some very common patterns that seem to pop up and take place in factoring trinomials. These patterns are very prevalent on the ACT. These are things that the standardized test makers expect you to know very, very well and expect you to recognize. So the quicker and better that you can recognize these patterns and know how to utilize them, the better. Now, the two patterns that we're going to be discussing are called a difference of squares and perfect square trinomials. Now, the first most obvious thing that we have going on here is a difference of squares is actually a binomial expression that can be split up into two separate binomials. This is different than what we did when we were factoring trinomials, where we had an expression with a trinomial broken up into two smaller binomials. Now, a perfect squared trinomial is a trinomial that is going to be broken up into two smaller binomials, but the special pattern with perfect squared trinomials is that you can get the same exact binomial for each part. So we'll look at each of these separately. We'll start with factoring the quadratic expression of a difference of squares, and sometimes called a difference of two squares. So if we look at example 3, and we're going to focus on part A, what we'll notice here is 4x squared minus 25. First of all, it's a difference of squares because it's a binomial, okay? And the word difference implies that it's subtraction. So keep in mind, this only works with a subtraction of two perfect squares. If there were addition in here, you cannot factor it. So if we had 4x squared plus 25, this cannot be factored. And we will discuss that in class in a little bit more detail as we go through this section. So keep in mind, a difference of two squares means it's got to have two perfect squares. So 4x squared is a perfect square, and 25 is a perfect square, which means it can be broken up into two smaller parts that are exactly the same. And then since it's a difference of two squares, it is separated by a subtraction sign. And so what happens in this process, and you'll notice in this pattern, is that the 4x squared can be broken up into 2x and 2x, the exact same term. The 25 can be broken up into 5 and 5, which are the exact same term. So we have two perfect squares. But what's special about this pattern is this. When we break up the difference of squares, you end up resulting into two opposite signs. So you have a 2x and a 5 for both terms, but each individual binomial, one has a positive and one has a negative. So it's very important that when you're doing a difference of squares and you break apart this binomial, you end up with two separate binomials that look exactly the same but with different signs. And so that's your first clue there on a difference of squares. Now, if I could just digress for a moment, I'll take you back up to our original problems where we were factoring out monomials. And if you look closely here at part D, you have u squared minus 4. Well, u squared is a perfect square. This can be broken up into two different u's. So that's going to go to u and u. And then negative 4, or in this case 4, can be broken up into 2 and 2. And since it's negative between there, we have a difference of two perfect squares, which means we're going to be left with a positive and a negative version of this. Now, if we're talking about the original problem, we have to keep in mind that the 4 is still a common factor, so we now have 3 factors if this is broken down completely to 4 times u plus 2 times u minus 2. So we factored out the common monomial first, and then we finished by factoring the difference of squares. So this is a good example of a difference of squares as well. So let's go back down to our difference of squares pattern. So you can see here that we break each individual perfect square apart, and then we break the sign apart into a positive and a negative. So that is difference of squares. Now, if we move on to perfect squared trinomials, it's very similar to difference of squares in the sense that we are dealing with 2 perfect squares on the outside, but we're dealing with a trinomial this time instead of a binomial. So what's going to happen here is this. We're going to break the 2 perfect squares apart on the outside, but what's going to happen is this time, instead of creating 2 different signs, it's actually going to create the same exact sign. So if we look at this, we're going to look at 9y squared and we're going to look at 16. Now 9y squared can break up into 3y and 3y, and then we look at 16, it can break up into 4 and 4. Now what I'm going to encourage you to understand, this example doesn't clarify enough, and I'll talk about this a little bit more, is that the 24y is going to break apart, and we're going to use the sign in front of the 24y as the sign in our final answer. So if we have a positive number there, we're going to end up having 3y plus 4 twice, and then we can write that answer as 3y plus 4 squared. If you notice in sample C, we have 49r squared, which breaks up into 7r, and then you have 1, which breaks up into 1, and then we have a negative value in front of that 14r, which is going to create a negative value in our final answer. Now, this is a trick or a problem that a lot of students run into. They simply only look at the outside numbers to see if they're perfect squares, and they immediately assume that it is a perfect square trinomial. Keep in mind that this pattern is very important, that the inside number is a 2 times the a value times the b value for it to work. So in this case, we have negative y squared plus 24y plus 16. If we break that up into 3y and 4 on the outsides, we must then multiply those values by 2 to get our 24 number. So that's the only way that it works correctly. If we had a situation where it said 9y squared plus 12y plus 16, that would not be a perfect square trinomial. So again, the quickest, easiest way to determine if you did this correctly or not is to see by going back and foiling the binomials to see if it comes back to the original trinomial. Now, again, factoring difference of squares and factoring perfect square trinomials comes with practice. You get faster with practice, and it gets easier recognizing these patterns with practice. Again, we will spend lots of time working on these types of problems in class. So, if you take this time to pause the video, there's 3 sample problems for sample problem number 3. So go ahead and work on factoring these different patterns. Okay, if we look at part A, it's clear that we're dealing with a binomial. That binomial has a negative value between the 2 terms. The 16y squared is a perfect square. The 225 is a perfect square. So what we have is we have 2 perfect squares being separated by subtraction. So this is a difference of squares binomial, which will allow us to break it up into 2 smaller binomials. So what I'm going to do here is I'm going to take each one separately. 16y squared breaks up into a 4y and a 4y. And then I'm going to take the 225 and I'm going to break that up, and that is going to break up into 15 and 15. So since we recognize that we are dealing with two perfect squares and we're dealing with a difference of squares, the pattern suggests that one of the final terms is going to be a positive and one of the final terms is going to be a negative. And that is going to give us 4y plus 15 times 4y minus 15. And that would be your final factored expression. Now, if you wanted to double check if this were a correct answer or not, you would simply refoil this, and you can see here 4y times 4y would be 16y squared. 4y times negative 15 would be negative 60y. And then if I distributed the second term, 15 times 4y is a positive 60y. And then positive 15 times negative 15 is going to give us a negative 225. Now, in the foiling process, we had to combine like terms, and this is what makes difference of squares such a special scenario. When we refoil this, what happens here is the middle terms, the negative 60y and the positive 60y, are common. They actually cancel each other out, leaving you 16y squared minus 225, which was our original expression. So this tells us, this is our check that tells us that we factored the original expression correctly. So you can see how whenever the positive and the negative value creates opposite terms in the middle, that's what makes the difference of squares special, a special pattern in factoring. So that's example A. Now notice example B and example C are both trinomials. So here we're dealing with trinomials, and of course we're dealing with perfect square trinomials. And if we look at the outside terms, 4z squared and 9 are both perfect squares. Now the way I like to work these problems, again, I like to take each of these terms and break them up individually. So 4z squared breaks up into 2z and 2z, and 9 breaks up into 3 and 3. Now, what we need to really do is just confirm that this is a perfect square trinomial by multiplying the 2 and the 3 times 2, because remember the pattern is a times b times 2. So if I multiply 2 times 3, that gives me 6, and if I multiply that times 2, that's going to give me the 12, which is the middle term that we need. Now that I've confirmed that, I just need to get my signs right. And so you can see here that there's a negative value in front of the 12, and so that negative value actually is going to be given to both terms. So this is going to be negative 3 and negative 3, which gives me 2z minus 3 times 2z minus 3. Now, anytime you have two terms that are exactly the same that are being multiplied together, you can actually combine those terms with an exponent. So if you look, if I multiplied x times x, I could make that x squared. Well, in essence, we want to do the same thing here. I have 2z minus 3 times 2z minus 3. Those are the same term, so I want to combine these terms together as a squared term, and this is a more consolidated view of the final answer. Now, it's extremely important that you get used to putting this as a squared term, because this will be an important process later on in chapter 5. So, perfect square trinomial breaks up into 2z minus 3 squared. And if we go to part C, we can look at part C. Again, we have a perfect square and a perfect square. So again, I like to break these up. 36w squared ends up being 6w. 20 and 6w. 25 breaks up into 5 and 5. And again, we look at the middle term. We're going to see that it's positive, but we also need to check that the 60 is correct. So 6 times 5 is 30 times 2 gives us that 60 value. So that tells us now that we can give each term the same sign as the middle term, which is a plus, which is going to give us two 6w plus 5 terms, which means we can combine those together and write it as a squared term. So 6w plus 5 squared is our final answer. And again, if you wanted to double check that any of this factoring was done correctly, you could come back and you could FOIL the two binomials that we originally factored to see if it came back to our original term. So very important that you understand difference of squares and perfect square trinomials, and that you can factor those comfortably and recognize them as they pop up. Alright, now let's move into what is probably going to be the newer factoring process that you've not seen before. This is a process called factoring by grouping. And what factoring by grouping does is it breaks a set of terms up into two individual problems where we will factor out a common monomial as we go through the process. So if we look here, we kind of give you a funny looking problem in this factoring by grouping, and it's got 4 terms basically. Excuse me. So we've got 4 terms going on here. Now this is just for example purposes. You won't always have 4 terms. Sometimes you'll be factoring trinomials using grouping, but we want to show you the process here first, the grouping process. So what we're going to do is we're going to look at these 4 terms, and what we want you to recognize is this. The first 2 terms, ax plus bx, have a common term between them. We could actually factor out a common x. But in essence, we want to separate them or break those apart from the second group of a plus b. So what we're going to end up doing is we're going to end up breaking these into 2 separate individual terms. Now, if you look down here in the solution, we've used parentheses as a method of breaking them up. So what we've done is we've just put a set of parentheses like this as a procedural step to helping us break these up. And this is why it's called grouping, because we've taken the 4 parts and we've grouped them into 2 individual parts so that we can actually factor out a common monomial. Now what you'll notice is in the first one we have a common x that we want to factor out, which gave us x times a plus b. Well, what we're trying to do here with the second one is we're trying to factor out something as well that's going to leave us an a plus b. So we can factor out a common 1. Now this is an important step because this a plus b and this a plus b are now a common term in the bigger scenario. So we factored out an x from the first one, we factored out a 1 from the second one, and we were left in both cases with an a plus b. So let's take this term here and this term here, and if we look at this, both of those are terms of the bigger problem, and they both have a common a plus b between them. So what we're going to do is we're going to factor out the a plus b, and when we factor out the a plus b, we're left with simply an x from the first one, and we're left with a positive 1 from the second one, and we've in essence factored this 4-term polynomial by grouping. Now, as always, if you wanted to double check this, you could simply FOIL a plus b back with x plus 1, and you would come up with the original term given in the example number 4. Now, this process of factoring by grouping is new and cumbersome at first, but after you do a handful of problems of factoring by grouping, it becomes easier and easier, and then in a lot of cases becomes the preferred method of factoring after many students have had the opportunity to practice it. And we will also use this in a second on some more difficult trinomial problems as we go forward. So let's take a look at an example here. Go ahead and stop the video and try sample problem 4. See if you can follow the process that I went through in the earlier example, and see if you can factor out these into 2 binomial parts. Okay, so if I'm looking at this, what I wanted to do with my initial factoring here is this. I wanted to break it up into 2 grouped parts. So I'm going to take the first part, x squared plus xy, and I'm going to break that up from the 2x and the 2y. So I've in effect grouped them off. I've broken it apart right there in essence, and I've grouped it off into 2 separate parts. Now, if I look at the first part, I notice that this has a common x that can be taken out. So I'm basically reversing the distributive process right here. So when I do that, I factor out a common monomial, and that leaves me an x right there and a y right here. So I've done this on the first part. I've factored out a common x, and I'm left with x times x plus y. If I look at the second group, I notice that I have a common 2 that I can take out. And it's a positive 2, so what I'm going to do is very important here that I bring out the plus sign with that. So when I factor out the common 2, I'm again left with x plus y. Now, this is an extremely important part of the process. We are looking in grouping to create a situation where we have the exact x plus y values on both parts. When we factor out these common monomials, we in effect still have 2 separate terms. If we look here, I have this term, x times x plus y, as one term, and I have a positive 2 times x plus y as the second term. So if I'm looking at these 2 terms as a whole, they have a common factor that can be factored out. I can actually factor out the x plus y. Now, when I factor out the x plus y from the first one, I'm left with simply this x. When I factor out x plus y from the second term, I'm left with this positive 2, and then I am left with these 2 binomials, which represent the factored form of the original term. Again, if you wanted to double check this, you could FOIL these 2 terms together, and you would be left with the original term at the beginning. So, factoring by grouping is a special factoring technique that we're going to use here in a second to help us factor more difficult trinomials. But it was important that you could see and understand the process on a simpler scale with 4 distinct terms, and so it's a little bit less confusing. Now, this is going to take lots of practice. If you don't get it the first time, that's fine. Just keep in mind that you're going to need to continue to practice this for it to be useful, and all of these factoring techniques are going to be extremely important as we move into Chapter 5 and Chapter 6 and Chapter 7 and Chapter 9 as well. So this one set of notes trickles through the entire second semester of Algebra 2. So all of these factoring techniques are going to be important to your success as we move forward into Chapter 2 and we start dealing with more in more difficult problems and different levels of polynomials. So let's take a look at how we can first use this grouping technique in factoring some basic trinomials. Notice, we're giving you a trinomial again, but the most important difference here is very simply the leading coefficient term. Notice in our example, the leading coefficient term is greater than 1. That is different than what we did earlier in these notes when we were factoring trinomials that had a leading coefficient of 1. When we were factoring trinomials with a leading coefficient of 1, we were only dealing with the outside constant term as far as finding the pairs of numbers needed to factor it. Well, now what's going to happen is we are going to have to deal with both the 6 in front of the x squared and the negative 6 as the constant. Now, unfortunately, over the years, whenever I was coming through Algebra 2, the way that we were taught to do this was through a guess and check method, where you went through a trial and error process of trying to figure out what were all the factors of the leading coefficient, what were all the factors of the constant term, and trying to find the combinations of patterns that would work to give you the middle term in the trinomial. Unfortunately, this process can be very cumbersome, and it can take a very long period of time to come up with the right pattern. Sometimes you get it on the first time, sometimes it takes you 12 or more guesses, if you will, to get the right combination of terms. So if you can learn this grouping process well, it's going to save you a lot of time and trouble. So let's go through the steps here of figuring out how we're going to use this grouping process. What we're going to do in the first step is that we're going to take the first term, the leading coefficient, and the last term, the constant, and we're going to multiply them together to get what we call our key number. Now, once we get our key number, negative 36, we're going to go through the same process that we went through earlier by trying to find all of the potential patterns of 36 that would multiply together to give negative 36 and then add together to get the 5 in the middle term. And so what happens is, again, you can start with your basic negative 1, 36, and then you could move on to 2 and 18, and you can see here that we're not getting close to that 5, so we would just keep working our way down. Now again, I would recommend using your calculator very wisely and proficiently here, and eventually what you'll get to is you'll get to a negative 4 and a 9, or a 4 and a negative 9. Now negative 4 and 9, or 4 and negative 9, both multiply together to give us the negative 36. But we need to figure out which combination of these two add together to give us a positive 5. And you can see that it's the negative 4 and the positive 9. So you can see that that's what we've done right here in step 2. We've made an effort to figure out which two numbers are factors of negative 36 that add together to give us a positive 5. Again, use your calculator effectively to make this process as quick and simple as possible. Now, this is where the grouping process begins. If you recall back to the previous example, we had 4 terms so that we could group it into 2 separate binomials. Well, we need to create that situation here. So what we're going to do is, we know that the negative 4 and the positive 9 created the 5. So we're going to take the 5x and we're going to break it apart into a positive 9 and a negative 4. So now we have created 4 terms. This is what we wanted to do to get our ability to factor by grouping. Now that we have 4 terms, we can treat this next step exactly like we did previously. We're going to take the 6x squared plus 9x minus 4x minus 6, and we're going to break it apart. And we're going to group it into two separate groupings. And you can see here in the first grouping, we're going to factor out a common 3x. In the second grouping, we're going to factor out a common negative 2. And then if you then look at each of these as individual terms, they both have a 2x plus 3 as their common term. So I'm going to factor out the 2x plus 3, which leaves me a 3x and a negative 2. And then I have my final answer of 3x minus 2 times 2x plus 3. And keep in mind, if you had written it like this, that would be just as good as well. It does not matter which order you put those in. So keep in mind either way. Now, how do we know if we're correct after this long, cumbersome process of grouping? Well, we could just simply FOIL back the 3x minus 2 times 2x plus 3, and we should come up with our original 6x squared plus 5x minus 6. So, what I think you will find after you do a handful of grouping problems is this process is much quicker than guessing and checking, which in my opinion is never a good way to do math. So, let's take a look at sample problem number 5. Go ahead and pause the video, and you can see that this has a leading coefficient greater than 1, so you'll need to use the grouping process. So go ahead and take your time to do that right now. Okay, so if you looked back at the previous steps, the very first thing that we wanted to do was find a key factor, key number. So the way we do that is we take the leading coefficient and we multiply it times the constant, which is going to give us a value of negative 30. Now, I could use my calculator effectively here, and I could take the negative 30, or the 30, and start dividing it by all of the potential factors, and 30 and 1. So I need to see which of these factors is going to give me a 1x in the middle. So we can clearly see that if I take 30 and 1, I'm not going to get 1. I'm either going to get 29 or 31 or something of that combination. So we're going to do 30 divided by 2, and that gives us 15. Again, 15 and 2 does not give us a 1. So 30 divided by 3, that gives us 10. But again, 10 and 3 does not give us a 1. So then I'm going to do 30 divided by 4, doesn't give us an even number. Then I'm going to do 30 divided by 5, and that gives me 6. So when we look at 6 and 5, we can tell very quickly that some combination of 6 and 5 would give us a 1. Now, the fact that the key factor has a negative in front of it, the negative 30, we have to take that into account. So we could say negative 5 times 6 gives us negative 30, and negative 5 times 6, and then we could have a positive 5 times a negative 6, and either one of these would give me a negative 30. What we have to figure out between these two is which combination of these when added together is going to give us the positive 1 in the middle of this trinomial. So we can see negative 5 and a positive 6 gives us the positive 1x. Now, we've found our terms. Now we need to create 4 terms out of these 3. So what we're going to ultimately do is we're going to break that positive 1x into 2 terms so that I can create a 4-term polynomial. So we're going to be left with 15x squared, and of course my 1x is going to be broken up into negative 5x plus 6x, and then of course I have to carry down my negative 2. Now, in doing this, I've created 4 terms, and this gives me the opportunity to do the grouping process. So 15x squared minus 5x, I can group that off. I can take the positive 6x and the negative 2, and I can group that off. Now as I look at each of these individually, I can see here that I can take a positive 5 out of this first one. So when I factor out the common monomial 5, I'm going to be left with 3x minus, excuse me, I missed a term here. I need to actually factor out a full 5x so that I'm left with just the 1 there. So don't make the mistake that I just made and just factor out the number. Make sure that you take out the full term of 5x. So we're left with 5x times 3x minus 1. Now, the second term, we can see here 6x and negative 2 have a common 2 in place. So I'm going to pull out a positive 2, which is going to leave me again 3x minus 1. Now this is extremely important. I wanted these two terms to be the exact same. So if I'm looking at this, I have term number 1 and term number 2, and what those two terms have in common is the 3x minus 1. So if I pull out the 3x minus 1, I'm left with 5x from the first term, and I'm left with a positive 2 from the second term. And I have my fully factored form of the trinomial. So that is the grouping process being used to factor a trinomial that has a leading coefficient greater than 1. This is going to take some time and practice to get accustomed to it, but if you do it and you learn how to do it well, it will save you a lot of time and heartache as you go through the remaining chapters in Algebra 2. So we've just gone through a long section of notes here. That covers all the different methods and ways of factoring. There are other methods of factoring trinomials, sometimes called the slide and divide method that you may have learned in Algebra 1. If you learn that method and you're more comfortable with it, that's fine. If you like grouping better, they both work just as effectively. So be sure that you get lots of practice factoring problems, as we will definitely use this throughout the entire second semester of Algebra 2.